just some remarks about the general line of our course. So we study the Toda chain system. We proceed to studying its generalization, which is called the full symmetric Toda system. And at the same time, we study some general approach, which is called the Adler-Kosten-Syme scheme, which is a general method to obtain integrable systems. And we will study this approach on the example of the full Toda system. So this is our primary goal for this lecture and the next one. I recall the last statement of the last lecture, which was the Adler-Kosten-Syme lemma 1. So we are in the context where some Lie algebra can be represented as the direct sum of two its Lie subalgebras, G plus minus R Lie subalgebras of G. We introduce some new bracket x, y, r on the linear space of G, and it is defined by the following formula: r, x, y, x, r, y. And we introduce the two Poisson manifolds. The first one is defined. So the manifold is always G star. So the dual space to the Lie algebra G. So it's a linear space, affine space. And on the space of polynomials S of G. So this is the space of polynomials on this linear on this affine space. And there is a standard Poisson-Lie structure which is defined by the Lie algebra structure on G. But now we will consider another Poisson manifold which is defined by the ring of functions and the Poisson bracket R, which is given by the same procedure as this Poisson-Lie structure given by the Lie algebra structure on G. But now we will consider this Lie algebra structure on G and consequently the Poisson structure on S of G. Okay. And then the first okay, and the next the lemma was the following. Lemma first was the following: let f and g be functions from this ring of functions, but additionally we assume that they are G plus invariant. You could understand it on the level of Lie algebras, but sometimes it's better to realize as the invariant function with respect to the action of the group, of the Lie group G plus. You understand that for each Lie algebra corresponds to some Lie group if they just consider the exponentials. In our case, we always stay on the level of matrix Lie algebra, so there's some subspace in matrices. You could consider exponentials, and they give you some group elements which act like element of group composition. So it is the same. So it's the same as S of G invariance with respect to the Lie group action G plus. And moreover, they commute. The Poisson commute with respect to the initial Poisson structure. Then F and G Poisson commute with the new structure. So this was lemma. But now I will demonstrate you another lemma, which is more coherent, which suits better to the case of Toda system, but which is of the same nature. So I need another algebraic interpretation. So let me consider the space, all this algebra of polynomial functions on the dual space, but I will decompose them in a little bit different thing. So I represent it as S of G plus G minus multiplied by S of G. Do you understand what is written? If not, it's better to discuss, because it's not complicated, but if you don't understand.
G minus multiplied by SG.
So this term means that we consider only monomials containing only G plus elements. And this means that we consider monomials which contains at least one generator of G minus. So for example, if G is SL2 and we decompose it as N plus B minus, this Lie algebra is generated by the element E12, N plus nilpotent up triangular matrices. There is only one element in this case. And here there are three elements, E21, E11, minus E22. Let's consider G2. And then this subspace is three-dimensional. And then, for example, if we consider some polynomial, some f from S of GL2, which is, I don't know, E1, 2, E2, 1, minus E1, 1, E2, 2. Suppose that this element is, this is G plus. So this is G plus, and this is G minus. In our case, there are no elements in this term which are which element of this subalgebra. Because so if I write here E12 square, then this decomposition, so this is an element of S of G plus, and this is element of G minus S of G. So because each monomial in this term contains an element of G minus. Here, this is an element of G minus. Here, whatever you want, this and this. So it means that there is some, if you want, how to understand, it's an ideal generated by G minus, by the linear subspace G minus. It's an ideal generated by G minus. It's not a Lie subalgebra, not a subring, but it's an ideal. No, it's a subring also. Okay.
So, sorry, what is exactly SG for?
SG?
Yes.
Do you know what is the tensor algebra of a linear space?
What?
Tensor algebra of a linear space.
Yes.
If you factorize it by, if you consider the symmetric tensor.
There's a tensor.
Symmetric tensor algebra.
Yes.
But it's just a ring of polynomials with generators given by the elements of this linear.
Yes.
Okay? So we have G, which is just the linear space generated by all these terms. And now we can see the polynomials generated with the letters which are generators. but it has an invariant definition as a symmetric tensor algebra of a linear space. Okay. Okay. What we need else? So I have this decomposition, and I'd like to define this projection as tau, the projection to the first term. If you want, it means that we restrict functions on the subspaces there G minus is equal to 0. So there is an ideal generated by G minus, and the I don't know what the subvariety given by this ideal. There, all functions from these ideals are 0. So there is this correspondence between ideals and subvarieties. So if you consider this ideal generated by G minus, it corresponds to a subvariety, I don't know, and G minus. So this is the subvariety in G, G star. So our variety is G star, and in this variety there is a subvariety on which all elements from G minus are zeros. Okay. This projection is the restriction of all functions to this subvariety. There is the Adler-Kostenheim lemma 2. Lemma 2. It is also called the Adler-Kostenheim's lemma. Let f and g are two invariant functions in S of g, like in the first lemma, and they commute, they Poisson commute with respect to the initial Poisson structure on the space. Then of f and tau of g else commute. So if we consider invariant G plus invariant functions in involution and consider the projections, they else commute. Here I don't make the sign, but whatever you want. So in fact, this is a subspace in this algebra, so we can think about it as a Poisson subalgebra. But you can place here G plus, because the images of these functions are now elements of S of G plus, and there is G plus Poisson structure on this space. So, but it's the same thing, because you consider functions with monomials only in G plus, so both Poisson structure coincide. Okay, there is such a statement, and let me prove it. Okay, it's principally the same calculation. So we know that f and g is equal to 0, and we decompose it. We decompose it in tau f plus f minus tau. I'd like to use the same notation. So the same notation. So f is equal to f plus f minus. And this is an element of this S of G plus, and this is an element of G minus S of G. And this is f plus plus f minus, g plus plus g minus. This is 0. And now I have to use this g plus invariance. It means, let me write it. I write it as f g plus, like the sum, like the Poisson bracket of two such summands with the first element, plus f plus f minus g minus. But this is 0 due to g plus invariance of the function f. And now I have to use the fact of the invariance of the function g with respect to g plus. It means that so it means that f plus g plus plus g minus is also 0, and it means that f plus g plus plus f plus g minus is equal 0. And so here it is f plus g minus plus f minus g minus. And I'd like to put this expression to here, but this expression is minus this expression. So it is equal minus f plus g plus plus f minus g minus. Okay? And for methodological reasons, I'd like to place them on different sizes of the equality. It means that f plus g plus is equal to f minus g minus. Okay? But both sides of this equality are elements of additional subspaces. So this is an element of S of g plus. In this decomposition, this is the Lie subalgebra, the Poisson subalgebra. And this subspace is also Poisson closed. So the Poisson structure of two elements from this subspace is also an element of this subspace. Is it clear? For this, it should be clear because it's just Lie algebra, Poisson algebra. So it is closed with respect to the Poisson bracket. But is it clear that this subspace is also closed with respect to the Poisson bracket? Okay, I will show just in a moment, but let us finish this statement. So this is an element of g minus Sg. So they are equal, but they are in different subspaces, which are direct summoned in this decomposition. So they are both zeros. So why this subspace is closed with respect to the Poisson bracket? So it's due to the Leibniz rule. So what is the element here? Let f and g be elements of g minus S of g. It means that f is the sum of monomials, and g is the sum of monomials, and each monomial, if I, is an expression of the form xi fi tilde, and gi is an expression of the form yi gi tilde, such that xi and yi are element of G minus. Okay? So each monomial has an element of G minus in its representation. I just written this. And it means that if we calculate the Poisson bracket of such elements J, just by the Leibniz rule, I calculate the Poisson bracket of each element with each. Let me write it. If it is not obvious, it is better to write. So there are 4 terms: xi, yj, fi, gj, plus xi with gj tilde, fi tilde, yj, plus fi yj xi fi tilde, sorry, gj tilde, and the last term plus fi tilde j tilde xi yj. So in all 3 terms here, we have an element from G minus. So these monomials are in G minus. Okay, or in G minus multiplied by S of G. But we know also that G minus is the Lie subalgebra. So the commutator of 2 elements from G minus is an element of G minus. So this monomial also contains a generator of G minus. So this monomial is also from this subspace. So this subspace is closed with respect to the Poisson structure, and by this consideration we obtain the lemma. Is it clear? Do you want some comments?
Why is xi you suppose that? And why the bracket of I and G plus is 0? I and G plus.
Which line?
I and G plus.
This one?
Yeah.
Because f is a G plus invariant function. It means that f, the Poisson bracket of f with all generators of this Lie algebra are zeros.
That sign means invariant.
No, invariance means that the Lie group acts by stabilize this function. But if you consider its infinitesimal action, it becomes the action of the Lie algebra. And the Kirillov constant Poisson-Lie structure, so we discussed this.
So what's the exact meaning of that sign on the power G?
There is an infinitesimal action of the Lie algebra on some linear space. Is it clear what is S of G plus? There is an action of G plus on G, the adjoint action. Let G be an element of G plus, and X is an element of the Lie algebra G. Let all group n algebras will be matrix group n algebras, Lie algebras. So in this case, the adjoint action of G on X is just a conjugation. I'm sorry, G. G minus 1 xg. But in fact, it's some fundamental question, and we have discussed it in the beginning of September. If you have some problems, please consult in the textbook on Lie algebras and Lie groups. But it is quite simple. So if X is a matrix, just JLN matrix, just matrix n by n, and G is an invertible JLN matrix. How the group acts on its Lie algebra by conjugation. Okay? If the element G acts on Lie algebra, it acts on polynomials constructed by generators of Lie algebra. Just it acts on all monomials, and it produces an action on polynomials. It could be understood geometrically, because there is a dual action on the dual space of the group. And if the group acts on the space, it acts on functions on the space. Okay?
Yes, so you needed the dual correspondence.
Yes. But it could be said in a more simple way, just by action on all monomials, on all just linear monomials.
Yes, if you take as metric, yes.
But then, if you consider that your G is an exponential of some t, you have the action of this element on your ring of functions, and you have the infinitesimal action if you consider the limit of t to 0. It is the action of the Lie algebra on functions. But you can understand it in both ways. But we have demonstrated that the action of the Lie algebra on a function is the same as the Poisson bracket in our Poisson algebra.
Well, when I think about Lie group and the algebra, I always think of the geometry side.
There are both sides in this picture. You can think about, you can choose the language. But this is the simplest one, up to my opinion. So, is it more or less clear that this means that f is G plus invariant function? But it's a fact that our Poisson bracket on this space it realized the action of the Lie algebra on this space. So if a function is G plus invariant, the Poisson bracket of this function with linear generators of G plus are 0. It's not obvious, but it's true. So it represents why we consider such algebraized function algebra. So it comes from the algebra. Okay, what else? Now we recall what is the full symmetric Toda system and discuss how it's related with the open Toda chain. I hope you solved the home tasks and this subject is more or less clear to you, but I would like to repeat. So full symmetric Toda system. We consider the Lux operator, which is a matrix with symmetric elements. But the symmetric elements will be the generators of B plus. I will write it. E1n, E12, E22, E2n, E1n, E2n, ENN. Eij are generators of B plus, which is a Lie subalgebra of GLN. Okay? The next step, we consider L minus lambda and the unit matrix. E11 minus lambda E12, E1n, E12, E22 minus lambda, E2n, E1n, ENN minus lambda. And then we consider the k chopping submetrics of this matrix, which we take the left lower corner of this matrix from which we have cut it k rows and k upper rows and k right columns. Starting from this, we consider the determinant of this submatrix. Determinant of L lambda E k. We'll denote it as delta k of lambda. If k is not greater than half of n, it is non-trivial polynomial. It depends on lambda. So if k is too large, so if k is greater than the half of n, when we don't intersect the diagonal, so in this submatrix there are no lambdas, so it doesn't depend on lambda. And I will introduce the coefficients of this polynomial. So it starts with lambda n minus 2k, and with the coefficient k n minus 2k plus lambda n minus 2k minus 1 k n minus 2k minus 1, etc. plus lambda 0 k 0. Theorem. Theorem is the following. We introduce functions kj, which is kj divided by ik0. So for k from 1 to n over 2, and from j from 1 to n minus 2k. R in involution, with respect to Poisson-Lie structure, Lie structure, in S of B plus. So B plus is the subalgebra generated by up triangular generators of J. Yeah. I suppose you have verified this statement in examples, but I would like to prove this theorem using the Adler constant sign scheme. But first of all, let us understand how it is related with the open Toda chain. So my statement is that Toda chain is invariant subspace, subvariety, is invariant with respect to the full Toda system. This part of the statement we'll prove later, but there are some simpler parts. So you remember that the Toda chain is defined on the space of Jacobi symmetric matrices, of 3 diagonal symmetric matrices, and the full Toda system is defined on the full symmetric matrices. The space is bigger, but I would say that if you suppose that all generators are zeros, except 3 diagonals, then this is the Poisson subspace. So the Poisson bracket is closed on this subspace. And so the flows of the full symmetric Toda system preserve the subspace. And some of these flows are just the Hamiltonian flows of the initial Toda system. So it's a good subspace in the phase space of the full symmetric Toda system. Like to say that all functions k, j equals zeros for k greater than 0 on the phase space of the Toda chain. So you remember that the level sets of Hamiltonians, of integrals, is an invariant subspace with respect to the Hamiltonian vector fields. So it is quite simple to demonstrate that the phase space of the Toda chain is a subspace of this level set. So let us calculate these functions when then the matrix is 3 diagonal. So let our matrix is 3 diagonal. B1, Bn minus 1, B1, Bn minus 1, 0, 0. We subtract the unit matrix, but now we start to chop the lines and the rows and the columns of our matrix, and then do it just for the first time. We get here we have some lambdas, but we have here the upper triangular matrix. Its determinant doesn't depend on lambda. Okay? So just the first chopping produces you an element which doesn't depend on lambda, so there are no coefficients. There are no coefficients. They are just zeros, such coefficients. So you see the Toda chain phase space is some subspace of the level set of Hamiltonians of the full Toda system. And another part which is also important, that the subalgebra, just the subspace generated by EII and EII plus 1, So how to say, you remember the Poisson structure in terms of the Flaschke coordinates. It is something like this, that A I B I is equal to 1 for B I and A I B I minus 1 is equal minus 1 over 4 B I minus 1, something like this. So the same Poisson brackets are realized on the subspace just of these generators of B plus. How to formalize this? I'd like to consider the ideal which is generated by Eij such that j minus I is greater than 1. Okay? So it means that I consider the ideal generated by all these functions. And then I consider the submanifold Mi. So it means that it is the submanifold of of B plus dual, which is given by this ideal. So it is the subvariety. There, all such generators are zeros. These generators are function on this space. Okay? I consider such an ideal the subvariety given by this ideal, and this calculation shows that these functions are zeros on this Mi. Gk for restricted to Mi are zeros if k is greater than 0. So it's the same thing that I demonstrated restricting our Hamiltonians to the Jacobi matrices, but written in a more algebraic geometrical way. Is it okay? And now I would like to say that this Poisson bracket restricted to Mi coincide with the the Poisson bracket in Flaschke coordinates with Poisson bracket in Flaschke coordinates. So this is the relation, but we will probably discuss this point more exactly when we understand better the geometry of the full symmetric Toda system. Next, I suppose you remember what is the Gelfand-Tsetlin approach. Some of you. Okay, but I will recall. I will describe. So now I'd like to demonstrate this theorem, and I need some algebraic stuff. I'd like to introduce the set of Lie subalgebras. 1, 2, Gillian, n minus 1. And these subalgebras are obtained from our Gillian-Lux operator, E11, E12, E1n. Now it is not symmetric, to better understand this strategy, I will say that we will consider. You remember in Adler-Kosten-Syme scheme there is always a decomposition of the Lie algebra into this direct sum of two subalgebras. So we will consider in what follows the decomposition of GLN as B plus SON. Do you remember what is SON? So firstly I will construct the family of functions here which are B plus invariant and which are in involution. And then I will consider their projection along SON to B plus, and it will be this function, the full Toda system integrals. So this is our strategy, and I will start with the construction of some functions in the symmetric algebra of SLN, which are in involution, which are B plus invariant. Okay, so it is the first step. E to 2, E to n, E n1, E n n. So now we are working here, and we consider such an algebra. An algebra given by generators in the right upper corners of these matrices. Okay. So this means that we chopped only one column and one line. Here the left one and the bottom one, but it's the same if you consider symmetric matrices. Okay?
Could we write as lower index to distinct?
Lower indices?
I mean, we still write
This?
yes.
It will be not evident. It's better. Okay? So this is GLN n minus 1. So when we have chopped n minus 1 rows and columns, and you understand that the element E1n, it generates the Lie algebra. Is it clear that it's a one-dimensional trivial Lie algebra? All commutators are zeros. But the next one is E1n minus 1, E1n, E2n minus 1, E2n. Is it clear that these generators are closed with respect to the commutator? So in fact, if you choose some rectangle in this matrix, the generators in the rectangle are closed, because then you calculate the JEKL, just commutator in the Lie algebra, EIL delta JK minus EKJ delta EL. So if you have two elements in the rectangle, the element here are else in this rectangle, because the indices are always the same.
You're using the same structure for the bracket.
Yeah.
This is the same structure that you use for the Poisson bracket when you define the
Yes,
generators of the.
Yes, of course, it was the definition. Yeah.
So it's like when you pass from the group to the algebra, then you can use the bracket instead of the Poisson bracket. You can use the Lie bracket.
They coincide only on linear generators,
Yeah,
but then you consider polynomials, and it is continued by the Leibniz rule. So, for example, then you can calculate E11 square plus E12 E21 with E12. So it's not an element of the Lie algebra. to calculate the Poisson bracket, you have to use the Leibniz rule.
Yeah, yeah. These components of the lax operator are a function of a parameter.
We consider them as functions.
Yeah, because otherwise then you cannot define the Poisson bracket.
We consider them as function on the dual space.
Yeah, okay.
Always. So it's a matrix. Those entries are functions on the phase space. As for example, when we considered the Lax operator for the Toda chain, open Toda chain, the coefficients of this matrix was just the exponential of coordinates. You remember, the flash coordinates were the functions on the phase space of our model. So here, the same story. So these letters are functions on the dual space. The Poisson bracket are the same as the Lie commutator, but then we consider polynomial functions of a higher degree. It's not the Lie bracket, it's the Poisson structure, which is given by extraction by the Leibniz rule. Okay, so, but here, when we work with only matrix entries, there is no difference of Poisson bracket and commutator in the Lie algebra. Okay. Is it clear that all these subspaces are Lie subalgebras? Okay. There is a very trivial thing. Then K is greater than n over 2. These Lie subalgebras are commutative. So if the corner is doesn't intersect the diagonal, the subalgebra is trivial. Okay. Okay, but we will consider the chain of Poisson algebras. So we always consider the symmetric algebra of these Lie algebras. n-1, which is the Poisson subalgebra GLN n-2, S of GLN 1, and S of GLN. The Gelfand-Tsetlin construction is concerns the centers of this K. So it's just the sum over K. Not the sum. So we would like to get the algebra generated by all centers of all these subalgebras. So I'd like to consider the algebra generated by all these algebras. Okay, from 0 to n-1. So Gelfand-Tsetlin approach says that this is a commutative subalgebra. If you take the centers of all subalgebras and generate an algebra by all the generators of the centers, but of subalgebras, it is a commutative subalgebra. Very simple and very important statement. So I'd like to construct the centers of such subalgebras, but even not the centers. I'd like to find some elements in the centers. So I will consider lambda minus e, L minus lambda e, and this k, which means the same thing. So we just consider E11 minus lambda, En minus lambda. We consider its submetrics. And when we defined delta k of lambda as the determinant of L E of k. So my statement is that the coefficient lemma, the coefficients of delta k are elements of the centers z of S, G, and K.
But isn't it this the same as we proposed in the last class, that they are Casimir functions of
What?
well, of the soft algebras, because in the last class we said that the trace is the Casimir function of GLM,
Yes.
and the last element was the Casimir function of B plus. So they are the Casimir functions of the subalgebras.
Yes, but some coefficients are not Casimir functions. You remember?
No.
For n equal 4, there is non-trivial there is non-trivial function which is not Casimir.
But they are always in the center.
No, Casimir, it means that they are central.
Yeah, but what does it mean?
There is a difference here. So, for example, if you chop just one element, you get a Casimir from this subalgebra. It is not a B plus subalgebra. What you obtain after you restrict this function to B plus, and became non-trivial integral of motion. So not else. So it's not the answer. The Casimir of some other Lie subalgebras, not B plus. We need we need an involutive family in B plus. So your question is very good. You started to understand the subtleties. Okay, so my first statement will be this one. So that all the coefficients of this partial characteristic polynomial of the matrix L are central elements of this strange Lie subalgebra. And I stress your attention here that it is not the same as S of B plus. There are some additional elements here. Okay? But how to demonstrate this one? I need some technical lemma technical. If we consider our Lux operator and calculate its Poisson structure with just the IJ generator. It's the same. Do you understand the notation? Because here it is a matrix, and here there is just a function. So all of this is a matrix. How to write it? So it is the sum of over k and L, E k L, L k L, Eij. So it's a matrix. Those matrix element is such Poisson bracket. Okay. And so the lemma state says the following, that it is the same thing if the commute this matrix with the matrix, but with the transposed indices. It will be your home task 1. Very simple and useful statement. But for me, it will mean the following. So we study some functions in. This is an element of S gln k. This is a function, and we would like to demonstrate that it is a central element of this Poisson algebra. But central means that it commutes with all linear generators from this Lie algebra, and it means that this function. So we need to prove the following thing: that delta k of lambda, I would like to write that it depends on L. Eij from this block is 0. But it means, so how we demonstrate this? We start to calculate, okay, I would like to say that it is equivalent to the group action, that if we act by the exponential of this Lie algebra element to the matrix L, it does not affect the function. I will write it. So the joint action of T Eij of L and calculation of this function is equal to decay of lambda on L. So this means that the function is invariant with respect to the group action. And here, what we have written, it is the action of this group on the matrix elements, of the operator L. Its infinitesimal form is written here. The lemma says that this infinitesimal action on the matrix elements is the same as the action on matrix units. So here it is the different thing. It is the commutator of EKL EJI multiplied by ELKL and the sum over KL. So this lemma allows to express the action of the Lie algebra element on the function by the action on the matrix. And it is quite simple to realize. So this action is the same thing as d lambda k of, I will write it like this, d Eji on L. I mean that it is an action of the matrix on the matrix part of the Lax operator. And this is quite easy to calculate. I will show you. Even I will make a more general calculation. I will consider an element G which has the form E0, some matrix B. I mean that here is K. Okay. G inverse is obviously such a form, B minus 1, but I don't need these stars. And then I'd like to calculate this adjoint action. You understand that we study G, L, N, K. So it's the upper part, this upper part. But after transposition, we get the left lower corner of this matrix, which could be non-trivial. And now I calculate the adjoint action of G on L, and I would like to calculate this function on this. Delta K lambda, and here I have to multiply the matrices E, B, E, star. Here I need this part. This is lambda E K part. And I'd like to multiply it by the inverse matrix E, B minus E, 0, 0, 0, star, star, star. To calculate this function, I have to calculate this part of the product and calculate the determinant of this part. This is dk lambda of such a function. E of add GL is the determinant of this block after multiplication. So this formula is not very good due to this notation. So this is more correct. The determinant of E0 star B L minus lambda E K, and when we multiply by this matrix, only this square works. B1 0 star E. Please verify the calculation. So this is the the hint, and this is the correct formula.
So to compute this, what do we need?
To compute this?
Yeah, to compute the final result.
No, final result is obvious because it's just the determinant of this matrix, determinant of this matrix, and determinant of this matrix. And you see, this is block diagonal matrix. So this is a determinant of B, and this is a determinant of B minus 1. But they are not inverse, these matrices. So it's quite a tricky calculation. The determinant are inverse. So it is the determinant of B, because the determinant of all these matrices is the determinant of B. Then the determinant of L minus lambda E K, and the determinant of B minus 1. So it is obviously the initial function of L. I think that this is correct, because the subtraction of diagonal matrix is supposed here. What do you say?
So from one hand, we need a well-defined Poisson structure to compute this Poisson bracket.
Yeah.
In order to compute that part. But in this part, what do we need? You know what information we need that is make the more convenient to use this part instead of the other part.
I replaced the calculation of Poisson bracket just by calculation of the action of the Lie algebra and the Lie group. And it was crucial. So first of all, this Poisson bracket is the same. So if this is 0, it's the same that the action of the joint Lie group preserve the function. The infinitesimal action is trivial. It means that the final action of the group, when you consider the exponential, stabilize the function. So this, I'm sorry, maybe it's better to write exponential of this. Yes, I'm sorry, exponential, and here else.
So then you need the exponential in the middle axis.
Yes. But here the exponential is just, so the exponential of the infinitesimal action of the Lie algebra. So this is the action of Lie algebra. You can exponentiate this Lie algebra action. You get some action of the Lie group. This lemma says that the action of this Lie group is the same as this action of the Lie group. So we can verify more simple statement with just matrix calculations. But it really uses the Lie algebras and Lie groups and the relations, how we can pass from one to another. So the but I suppose you know this, that if you have the Lie algebra, you can exponentiate it to get the Lie group. And if you have the Lie group, you can consider its tangent space at the unit element, and you get your Lie algebra. Maybe not non-trivial thing is that if the action of the Lie algebra is 0, then the exponent, the action of the exponential, stabilize the element. Is it not evident? Is it evident or not evident? I can give you some comments about this, but if this is correct, so if we replace the action of the Lie algebra by the action of the Lie group, and then we use this theorem to express this action of the Lie group by just the matrix conjugation. So if this is correct, do you principally agree with this calculation? Okay, so we will discuss just today. Okay, so we demonstrated by this consideration that all these elements are central function in this subalgebra. So the family, or the complete family of such the coefficients of these elements is an involutive subalgebra in JLN. So delta k lambda, do you remember it is lambda n minus 2k e k n minus 2k, lambda n minus 2k minus 1, k n minus 2k minus 1, plus L lambda 0, e k 0. So the first corollary is that the whole set of ki is an involutive family n S of GLN. It's the consequence of the Gelfand-Tsetlin idea. Do you agree? So all this family is obtained as an aggregation of centers of subalgebras. We have a tower of subalgebras, of Lie subalgebras, of Poisson subalgebras. In each subalgebra we consider central elements, because all these coefficients are central in some subalgebra in this tower. And we just combine all these elements, and I claim that it is an involutive family. Do you remember what is also needed to use the Adler-Kosten-Sym lemma 2? Invariance, yes. So I'd like to recall you that we consider GLN as the sum of B plus and SON. And we constructed a big family, a big involutive family in this subalgebra. There is a projection tau here, and we need to choose between these involutive functions B plus invariant functions. We have to find B plus invariant functions in our family. After that, we will just take the projection to the symmetric part. So it will be just the symmetric, we will discuss it. But first of all, we need to find B plus invariant functions between these functions. So we have to calculate the action of the group B plus, how B plus acts on delta K lambda. So we will consider the joint action of the element G from B plus on L and calculate this function. And it is the same as to consider of lambda of G transposed L G transposed minus 1. This is due to lemma. Now I will write it. So it is delta K of lambda of A, B, C. Sorry. the determinant. So we have to subtract lambda on the diagonal, and then calculate this corner of the resulting matrix. I pretend to such a formula, L minus lambda E k B minus 1 0 star C minus 1. Okay, so this is equal to what equal that A divided that C delta K lambda L. And this is already a result. So you see, then you act by borrow element on our Lux operator. The delta K, which is a polynomial on lambda, it is multiplied by a constant. Okay, so it means that the ratios of coefficients of this polynomial are invariant, are B plus invariant. E k I, E k j are invariant functions, are B plus invariant. Okay, we stop for the coffee break and continue after 15 minutes with this seminar part.